Okay, I'm recording. By the way, I'm recording everything in the class, all the lectures, and I post all those videos. Please spend some time on it. Okay, you can rewatch the video and spend some time studying it. Okay, you have all the resources here. Okay, I just posted a set of homework problem of chapter 2 on Moodle. We're not done with chapter 2 yet. I just posted it in advance. If you're interested, you can start looking at it, reading it. Okay, but it's all right. It's not required yet. Okay. Let me share the screen there. Okay, can you see it? Anybody? Give me a response. Can you see it?
Yes, we can see it.
Okay, sounds good. Okay, let's review it. We have halfway through that problem, but we're not finished yet, right? So it is a ramp, right? 20 degree. You have a package, a board, 1 by 1 meter. Okay, try to control the movement of that board by adding some oil fumes in between the board and the ramp. Okay, so we try to control the movement, control the speed. We want it slide down with constant speed, 2 centimeters per second. Okay, constant. So the way we attack the problem is this, right? We draw free body diagram. We pick the board to draw the free body diagram first. Okay, the board. So I spent some time showing how to draw the free body diagram. I hope everybody know how to do it. Okay, so when you detach an object from the other object, which in this case you detach the board from the oil film. Okay, then you have to replace by an internal force between the two objects, between the board and the oil film. Okay, since you take the oil away from the drawing, then you have to replace by a force to represent the presence of the oil film. Okay, that's a rule of thumb, very, very important on drawing free body diagrams. You have multiple objects always. Okay, so but when you draw free body diagram, likely you probably will draw one object at a time. Okay, so that's how to make it correct. Okay, so in this object, the board, you have a weight. You have weight, 2 components of the weight, W1, W2. Okay, you should be able to calculate W1 and the W2. The counter force will be the supporting force, which in this problem doesn't matter to us. We're not calculating that. If you want, you can still calculate N, no problem. It will be the same as W2, okay? However, in this case, W1 is very important to calculate because W1 should be balanced with the shear force, F tau. Okay, which is very, very important for this case, for this problem. We need to calculate the shear force, resistance force between the oil film and the board. Okay, so that's what we do. After we draw the free body diagram, I want to emphasize that's a part I want to check in the test or quiz, the free body diagram. Okay, you have to draw it correctly. And then I want to check this. The equation you provide, is that correct? Okay, you don't have to have a complete, the fully expanded equation with all the variables. I want to general that equation. Show me the direction, okay, when you solve the problem. You pick a correct equation, basically. That's the very, very important first step of solving an engineering problem. Okay, you will have a dictionary of equations at the end. You already had a lot. You have many engineering classes. Okay, so when you see a practical engineering problem, the first thing is, you draw the free body diagram for you to understand actually the problem. Okay, then pick the correct equation. Okay, then so these are the priorities. So I give points for those priorities. Okay, then after you get this equation expanded, Okay, easy. In this case, the x direction force balance, right? Oh, then F tau equals the W1. So because we can calculate W1, we should be able to calculate the shear stress. I'm sorry, shear force, F tau. Okay, we ended on there and on this last time. Now, here we have nothing to do with the 2 centimeter per second speed yet. Okay, so this force, this shear force, ensure that we will have a constant speed to slide down, which is one of the sticky point for this problem. You have, if you're an engineer, you want to make sure it slide down with constant speed. Okay, so that's good. Then next step, now let's look at how to ensure the 2 centimeter per second. Okay, now we have to look at the other object for this problem, right? Is that right? Okay, so what is the other object you want to look at? You want to look at the ramp or you want to look at the oil film? Okay, you're engineering future, right? You need to make decisions on solving problems. If you choose a wrong decision, maybe cost you more time or even wrong answer, right? So answer me, which object you want to look at, the ramp or the oil field? And what is your reason to make that selection?
The oil film?
Or why you pick oil film to look at?
Because it should be the only other thing with forces acting on it.
No, why not the ramp? There's a force on it too, friction between the oil and the ramp. Why you pick right? Yeah, you know, common sense, educated guys, right? Common sense, that's right. You should pick oil to look at next. But what is the reason? You know, I want you to be clear why you do that. And in the future, in other problems, you also have the correct reasoning or making some selections.
It's the only other thing moving.
That's right. I think I like the word moving. You have to relate it to the 2 centimeter per second. Okay, the ramp is not moving 2 centimeter per second. It's not even moved. It's there. So if you look at the ramp, then useless, right? It's a movement you're looking at. In here, there's also no movement. In this board, there's nothing moves here. It moves itself, but we didn't count any information of the movement here. Okay, so you have to pick something that actually related to the 2 centimeter per second. Okay, so okay, if you decide to pick the oil, I want you to draw a clear oil, the clear object. You want to exaggerate it, right?
Professor,
Yes.
why did you change it to centimeters?
Huh? What?
Like, because in the book it says 0.2 meters.
0.2 meter? If it's 0 meter, 0 meter, doesn't matter to me. It's just a number. I remember. I thought it's 2 centimeter per second.
Okay, and why does
hold on. 2 centimeter in my book it said 2 centimeter per second. Which book you are reading?
I was reading the fluid mechanics one, the one that you gave us. It says in the problem statement it says 2 centimeters per second, but like in the actual problem it says 0.02 meters per second.
What means natural? Did I wrote 0.2 meter per second? I wrote here 2 centimeter per second.
Yeah, yes, sir. Yes, sir. I understand you did that, but I was just wondering, is there a difference between the two?
We could convert it whenever. Doesn't matter.
You can convert it to meter per second, sure, but it's not 0.2 meter per second. Do you know how to convert from meter to centimeter?
Yes.
How many meter per second? Let me ask you this.
Yes,
2 centimeter per second.
I know to convert. I was just wondering, like, is that a reason why you did it on that process or at the end?
I did. I haven't converted to the speed yet, right? So if you want to convert, it is 0.02 meter per second. I haven't done it yet. I don't know what you're looking at. Did you look at the notes from the previous semester or?
No, sir. Never mind. It's all right.
Okay, no problem. It's not 0.2 meter per second. Okay, it is 0.02 meter per second. Yes, if we start to working with the film, which I'm going to do in a minute, you need to use the meter per second as a unit because that's a standard unit. In the calculation, in all the equation in the SI system, you have to use meter per second. Okay, in the book, the problem statement, it gave you 2 centimeters per second. It's a little bit confused, try to confuse you. Okay, you have to convert into 0.02 meter per second. Okay, is that clear to everybody? Okay, did I answer your question?
Yes, sir, it did. Thank you.
Okay, okay. I haven't talked about it, right? Yeah, I'm about to say it. Okay, so now the speed of the board going down is 2 centimeters per second. Okay, how do we draw the free body diagram of the oil film? Okay, this is the kind of like the dynamic problem, right? For the first object, the board, what we trying to do is actually fully statics. Okay, although it moves, but it's a force balance. So basically, this is the static problem process. There's no velocity there, right? It's just a force balance. Okay, so but here, this film actually move and change shape, right? So what can we draw on free body diagram? Okay, what is the rule of thumb? I mentioned it earlier. I'm drawing free body diagram. When you detach it from another object, are you detaching it from the surrounding objects? When you draw a free body diagram, you're not drawing the board on this. This is the oil film. Okay. So are you drawing the board on it? At least I am not. Okay. So I detach this oil film from the board, basically. I take it out. I just look at it individually. But it's actually connected to the board. Okay, on top of it.
Still applying a force to it.
That's right. You have to have the force draw on your free body diagram to represent the presence of that board. Okay, you can't just get rid of the board, right? It's there. So you have to take into account that effect. So action reaction, right? Look at this. This shear force F tau. Right? The shear force F tau is from the oil to the board. It tries to stop the board from moving down. So to action reaction, what happened to this oil film? So the presence of the board apply a reaction force to the oil film, which is exactly same number. Is that right? But with opposite direction. Okay. So force balance. So for this problem, the ramp doesn't matter, but the ramp also give a resistance force here, right? Okay. For our problem, I don't care this one, but if you look at the force balance, you should put another force on the ramp. Okay. Okay. It should also be balanced. Okay, if you don't consider the weight of the oil film, but if you consider the weight of the oil film is very, very thin, you know, we can just neglect the weight. But if you consider the weight, you have a weight, you have components, so you should have a force balance also. Okay, so so here, come back here. So we're gonna apply our equation, right? Which equation so far we learned? This is the viscosity problem, right? Shear stress problem, right? Is that right? What is the equation?
Isn't it shear stress is equal to mu dy dv?
Yeah, du, not dy dv. It's du dy, velocity gradient. That's called velocity gradient. Okay, I assume everybody did the calculus 1, 2, 3, fully understand the meaning of those derivative integrations. Okay, If you don't, let me know. We talk about it here. This is the changing, the rate of the change of velocity along the y direction, which is what? Y is this, right? Is that right? That's about y direction, vertical direction, okay? Changing of velocity along y direction, okay? So shear stress, look at this. What is the relation between shear stress and the shear force? On the free body diagram has to be force, okay? Stress is per area, right? Just like pressure, okay? But in the free body diagram is a force diagram, so it has to be force. So what's the relation between F tau and the tau?
Are they both forces?
No, shear stress is a stress.
Oh, okay.
What means stress? Stress means, I already said it. Please pay attention to what I said if you don't understand, okay? Stress is force per area. Just like pressure. Pressure is a normal stress. Shear stress is horizontal, right? Shear stress. Okay, so pressure is force per area. Do you agree? Okay, you have to pay attention to in my class, 100%. It's only 1 hour, 15 minutes, right? I save you a lot of time learning outside the class, okay? Just please stay with me, okay? Shear stress is force per area. Everybody, give me some response.
Yes, sir.
Okay. So area, okay, force per area. So what is area you're talking about? Are you talking about the surface area of the board, you know, with the oil film, contact with the oil film, right? You put it in under the board, filled with the oil, right? Is that right? So can you, now, we calculated F tau last time. What is the value of F tau?
8.5.
8.5, right? F tau is 8.5. Action reaction, just opposite direction, okay? So can you convert your F tau to shear stress? What is tau equals? Huh? Anybody?
Force divided by area.
Okay, in this case, F tau divided by area. So give me a number.
Be 1 squared, right?
Yeah, so what is the tau? What is the shear stress value?
8.5.
Okay, what is the unit?
Wouldn't it be
Newton per meter squared.
Newton per meter square. Okay, everybody got it? Shear stress, easy. You can just calculate based on the shear force you calculated in the previous part from the board. Okay, so, okay, good. So 8.5, let's apply this equation, equals viscosity. What is the viscosity? Is it given? Here it is, 0.05 Newton second per meter square, right? 8.5 Newton. Let's put the unit always, make sure it's, you know, engineer, we have to be strict, right? 0.05 Newton second meter square, right? Times, okay, du dy. How to construct the du dy? What does that mean, really? Okay, now let's come back. This is the sticky point, right? It's a new thing for you. So what is the velocity inside the oil film? What is the velocity distribution looks like inside the oil film? Okay, now let's come back to the physics. What is actually the physics in here in this oil film? No, fluid mechanics, right? It's difficult to see. You cannot visualize it. You can see the movement sometimes. Okay, so but can we describe it?
Yeah, it's gonna be more. It's gonna be more fluid at the top, and then we're slowly.
Exactly. More fluid in the top because in the bottom it connected to the ramp, Okay, we mentioned last time non-slip boundary condition. Remember, I'll give you an example: flow over a plate. At the bottom, when you connect to the board to the surface, you have 0 velocity. Okay, it's called non-slip boundary condition. Always that like that. It's exactly on the surface. There's no velocity, 0 velocity. Okay, do you agree? Basically, it follows the surface. Okay, so what is the velocity on the top surface of the oil film?
The same velocity of the board.
The same velocity of the board, because on the top surface, it sticks with the board. The board moves down at the 2 centimeters per second. That's what you design, right? If it moves down 2 centimeters per second, in the top of the oil, it's also 2 centimeters per second. Okay, so you get the 2 boundary condition. One is on the top of the oil, move down 2 centimeters per second. The bottom of the oil, not moving at all. Okay, is that right? First of all, do you agree with this, everybody? How many of you? 17, 18 of you? I have 17 of you in the class today. That's good. The total, we have 19 students, only 2 missing. Okay. Everybody agree? The 2 boundaries. Okay. So what's in between? It's a gradually change, right? That's the 2 limits, to the maximum and minimum. So in between must be less than 2 centimeters per second and greater than 1 centimeter, 0 centimeter per second, right? Is that right, everybody? Educated guess, right? It has to be gradual change. It may not be linear, okay? If the thin enough, it's close to linearly change. Okay, if it's thicker, then it might not be linearly change from 0 to centimeter per second. But actually in this problem, you don't get too much. Let's assume it's linearly change. So that's the velocity distribution looks like inside this oil film. Okay, very important. After you take this class, you need to, for the common cases, you need to know what the flow looks like. Okay, okay. Is that right? Everybody with me? Okay, okay, good. Okay, now, can you describe a du dy for me? You see, this is along y direction, right? Du dy is the changing of the rate of change of the velocity along the y direction. Do you understand? Is that right? The rate of change. Okay, so in calculus, we know we do this, right? Delta u over derivative, right? Is that right? We know that du dy is similar to delta u over delta y. Is that right? Delta, what do you mean by delta?
The change.
The change. What means delta y then?
The change in the y direction.
Okay, so usually this is not equals to du dy, right? This is not equal. Okay, so how to make them equal? That's the definition of the derivative, right? Take a limit when delta y tend to be very small, infinitely small. Then they are equal. Is that right? This is not the first time you see this, right? Okay, if that's the first time you see this, then you're in trouble. So that's the definition of du dy. So okay, so here I don't have a function of velocity in terms of y. So okay, so I cannot directly differentiate it, but I probably can use this process. Delta u over delta y, limit when delta y intend to be close to 0, then they are equal, right? So in this case, it's a very thin oil film. Is delta y very thin, very small? Yeah, it's kind of yeah, it kind of satisfies this condition. Okay, it's equal. So it's exactly perfect application for using delta u over delta y to represent the du over dy. Okay, so that's the justification. We are engineer, we make decision. It's not like whatever decision we want to make. No, it's not. It's based on the condition that does this satisfy. Okay, you need to make sure you are the gateways to make sure those conditions satisfies. Okay, so we will use delta U over delta Y to represent the du over dy. Okay, since the film is very, very thin, delta Y is very, very small. Okay, so what is delta Y in this case? Oh, okay. I think delta Y is our unknown, right? Is that right? We're trying to find the thickness of the oil film to make this happen. Is that right? How great is that? Our unknown is in our equation. Great, we can solve it. That means we have a right direction, correct direction. Okay, our H is our delta Y. It's the thickness of the film. Okay, so along that thickness of film, what is delta U? What is the velocity difference?
2 centimeters per second.
Just 2 centimeters, because this is 2 centimeters per second. This is 0. Delta U is just 0.02 meter per second minus 0, right? Okay, is that right? Everybody follow me?
Looks like you wrote 0.2.
I said 0.02. You see, I have a 0 here. Okay, bear with my writing. 0.02 here. Okay, meter per second minus 0. Here you go. Then we have this equation, which has our unknowns in the equation. Okay, can you solve it for me? What is the thickness? Hey, look at this. Your 2 centimeters per second is included here. You know it's correct, okay? So that thickness will ensure you have a 2 centimeters per second speed. Okay.
What I got is extremely small.
Yeah, it should be. That's why we have this. We can freely use this. Otherwise, you cannot use du dy to delta u delta y to represent du dy. It has to be small, right?
It's 0.000117.
Meter? 0.00 zeros after the decimal?
Yes, sir.
Okay, so how many millimeter is this? If you talk about small units, we use millimeter, right?
0.117.
0.117 millimeter. Okay, 0.117 millimeter. Okay. Yeah, that's reasonable number. It has to be really thin. Is this comparable to the diameter of your hair? I think it's comparable. It's about the thickness of the one hair. Okay, one human hair. Okay. So hey, we solved the problem. Okay, seems like a complicated problem, but hey, divide and conquer. You have to have a procedure to solve any engineering problem. You can have a process. Okay, it's not like, oh, this problem is difficult, this problem is simple. Every problem is the same. Okay, you follow the rule, follow the procedures, it should lead you to the answer. Okay, that's the point I want to convey. Okay, so we calculate based on the force balance for the board. We calculate the shear force between the board and the oil. We use the shear force between the board and the oil to find the shear stress. Then we can calculate the velocity gradient and the thickness. Okay, so that's the process we take. Okay.
Dr. J,
Yeah.
whenever we were finding the shear stress, why did we just say that the area was just 1 meter?
It's 1 by 1. I'm talking about,
okay.
see, I look at this. I have meter squared down here, Newton per meter square as a unit.
Yeah, because the area was given in the problem, right?
Yeah, area is given in the problem. 1 times 1 meter.
Okay.
Square. Basically, 1 meter square is the area. Okay. Oh, by the way, let me ask you this. How many of you have textbooks? How many of you don't?
Mine's coming in. We ordered it.
Okay. That's good. And I was told, I'm not familiar with it. I was told that the new thing they posted on Moodle, in the class Moodle page, some online textbook. Did you see that?
Talking about that red shelf? or
Yeah,
whatever.
ratio. Yeah. Is our textbook in there? I just try to save you some money. If our textbook is in there, then maybe it's cheaper. I don't know. Did you know, any of you checked that ratios?
Yeah,
How much is our textbook in the ratio?
something $40, I guess.
Oh, it's only $40?
It's like
Yeah,
$30
but,
to $40.
It's just you are just renting it for 3 months. You are not buying it.
Oh, okay. It's renting. So, but it's, hey, go ahead, guys. It's 40 versus 250, right? If I were you, I would rent. I don't keep much of a textbook nowadays. You know, everything is Google. You know, you can find all the knowledge online. So, okay, it's up to you. But so okay. So that's you can get a little bit cheaper textbook rental. You know, from there. Okay, good. Let me ask you one question. Continue on this problem, extending on this problem. So now let me ask you this: if you wanted the board to move faster, do you want to increase the thin film or decrease the thickness of the film?
Decrease.
Why? What is just that? Please don't answer too fast. Think through it first. You have a justification. That's a good habit for engineer. They ask a question, don't answer. Okay, people will take your word and sue you later. Okay, so
I meant to say increase. My bad.
Increase? Why is that?
Because if you increase the amount of film, that's the less resistance of the ramp that's going to be applied to the board.
Okay, let's come back to what I will write up here. Okay, I think I like what I wrote down here. It's very clear engineering steps here for this problem. Can you use the equations we use to explain why, if you want to increase the speed of the board, you have to increase the thickness? Which equation tells that? Okay.
Wouldn't that be the limit?
Huh?
Wouldn't that be the limit?
This one, you say?
No, the limit of delta U over delta Y.
This one? Why this tells you increase the speed, you want to increase the... Yeah, I understand what you say. You're kind of right. You're kind of right. Okay, yeah, you're right. So you from this, actually, I will look at this equation. Okay, so it's 8.5. Will the 8.5 change if you want to make it faster? See, when you calculate the 8.5, what did you use to calculate the 8.5 shear stress between them? You calculate use this, right? Is the 2 centimeter per second, that value is used in this process to calculate the 8.5?
No, sir.
No, right? It doesn't matter. This equation, 8.5 is to ensure a constant speed going down. It doesn't matter what constant speed, what's the value. So only thing here matters is the h here, right? So in this equation, 8.5, doesn't matter increase or decrease, it won't change. This one won't change, okay? Viscosity won't change, okay? The only thing could change if you increase the speed is this term, the last term. Okay, which is, you're right, you answered right, which is from this, okay? So if you look at this, if you are on increase into 0.04 meter per second, 4 centimeter per second. So for this term, if you increase the numerator, you have to increase the denominator too to make it the same value, so that it will be equals, this equation will be equals to 8.5, the shear stress. Okay, is that right? Okay, so that's the logic behind. Okay, so you look at the equations always. Don't right now you're at higher level. You know, you're close to an engineer. It's engineer. Don't say anything based on your common sense or whatever. Go through the math first. Okay, it will ensure your answer is correct, because people will make you accountable for whatever you say. So make sure whatever you say is correct before you say it. Okay, so that's the reason why increase the speed, you have to increase. So you can really control. Okay, if you want to move down faster, just increase the thickness of the film. Okay, if you want to move slower, decrease the thickness of the film. Okay, so That's this problem. I like this problem. It's a really good problem that related to the design process. It's not really just, hey, solving a problem and on the paper. You know, everything you do here, you learn, we try to have it connected to some reality, right? Real application. And that's the design process. Similar design process you probably will go through in your career later, okay? So any questions for this one? I want everybody, 17 of you, 100% understand this problem. That's the starting point. You will see more difficult problem later. Any questions? I have time. I don't want to slow down. I don't want to rush. I want to make sure everybody fully understand. It's okay if you don't understand now. We talk. Any questions? Which part is not crystal clear to you?
On the last page.
Okay. Which one? You're not clear.
No, I meant on the page before.
Oh, previous page. Okay, yeah.
Did we only ever use f of x to find the force of tau? Did we not use f of y?
What's the question again? Can you repeat?
Did we not use the sum of f of y to help find tau? Do we only use sum of f of x?
Yeah, we just need the sum of. You don't need the sum of the y. If you want to, you can, but you don't have to use every equation, right? But we just need to know f tau. You don't need to go through the vertical times a coefficient or something like that. I don't have that coefficient for you. So you have always multiple ways to solve a problem, right? Is that right?
Yes, sir.
We don't need the vertical. If you want to, you can just simply calculate the n equals W2. You can calculate W2, right? It's just sine, cosine 20 degree times 25 times the weight. Okay, so no, you know, but you don't have to use every information. Okay. One more time, any more questions? Okay. You truly understand, fully understand? Okay, if you fully understand, let's do a quiz now. Okay, I turn this page off. Okay, I want you to close your book, and I just want you to repeat what I did and solve this problem on your paper. Take out that blank paper, write it down, start from the free body diagram. I want to finish on one page. Okay, then take a picture and submit that picture into Moodle. That's our first quiz. I just want you to practice it to make sure your system works technically, computer-wise. Okay, know how to submit and how to write, how to take a picture and submit a picture in Moodle. Okay, it's just a practice. I know everybody gonna get a full point on this. Okay, except the two missing today. So, but listen to me. I don't want you to copy whatever you have on the textbook. If you copy the textbook, you will absolutely get 0 points. Okay, I want you to follow my way. I want to look at the two free body diagrams you use for this problem. I want you to write the correct equation. Okay, it's from the general equation to the extended equation to solve the value. Okay, for both parts. You have two parts, right? Two diagrams for this problem. I just want you to exactly follow what I wrote down. Okay, so if you write notes, just copy your notes. If you don't, just try to figure out yourself. Okay, see if you remember. Okay, if you don't remember those values, you can ask me. I can write it on this blank paper now. Okay, so I give you from now to the end of the class to complete that. I want everybody 100% get this quiz. Okay, I don't want you to miss any. But when I grade it, I really will grade all the diagrams, all the equations. Any mistake, I will take points. Okay, even the diagram is something not clear, didn't use the letter, all those things, it will be, I will take some point off if you didn't make it 100% correct. Okay, so you have plenty of time. I have maybe 27 minutes now. You have plenty of time to write it down and take a picture and submit to Moodle. Okay, go ahead now.
Just
Turn on your video and please do it yourself. Yep, any questions?
just to clarify,
Yeah.
0.02 meters per second.
2 centimeter per second. So it's 0.02 meter per second.
Thank you.
You're welcome. Okay, I'm going to Moodle and open the submission site. Okay, this is our first quiz. It is a surprise
I
quiz.
was,
Some of quiz will be like that. Okay. Yep. What's your question?
I was looking to see if you could write the givens in the problem again, since you told us we didn't have to take notes because you posted on Moodle. I didn't write down the problem.
Yeah. What do you want to know? Okay. So basically, this is a test to see if you listen to me, listen to my lecture. Okay. So I can give you the information of the problem. Okay. So this is a ramp. Okay. 20 degree. There's a
We have to
film.
write the actual values, or can we just write the like tau solve tau equals mu du dy?
Yeah, you need to solve to the final solution. Yeah, I want it. So 1 by 1 meter square, that's the area. Okay, so I want you to calculate the thickness of the film H, right? The moving speed is 0.02 meter per second. Okay, so what else? The viscosity is 0.05 Newton second meter square. Okay, so I guess these are all the values you need. Okay, the weight is 25 Newton. The W is 25 Newton for this object, for this block. Okay, go ahead. I just wanted to practice the summation process. Okay, we're gonna do this kind of things a lot.
You want to submit it as a PDF?
It doesn't matter, as long as image, PDF, all okay with me. But use common format that I can open.
Yes, sir.
Okay.
So we can write the units at the last of the solution, or just write in every steps.
You write every step. I want every steps. Okay, every step I showed you. I don't want to. If you even give me a correct answer but miss steps, I still take point off. Okay, I want to see your steps instead of actually the final answer.
No, but I'm talking about the units. You want to write units in every step.
You need to get unit. Yeah, please put the units in those steps, in those equations. That would be good as an engineer. Okay, for all the statement, please keep the units.
What are the units of viscosity? I can't read it. Sorry.
Oh, that's all right. Newton second per meter square. You have a summation due time is 10:45 today. Okay. Please make sure you finish it like at least 2-3 minutes before that due times. Some your summation take a little time. It's possible. So yeah, be sure. I want to make sure it's fair so everybody have the same deadline. Okay. You don't tell me I cannot submit or something after the class. Please try to do it a little bit earlier. You have plenty of time for this. Yeah, it's already posted on Moodle under topic 4. Okay, quiz 1.
I have a question.
Yeah, sure.
Is that 1 by 1 meter square area?
Yeah, 1 by 1 meter square. Yeah, if you have any question, let me know. If you're not clear of the value or whatever, yeah, let me know. Okay, I don't see video from Jamal Woods. Anish, okay, please turn on, keep your video on, especially when you're doing the quiz. I know the situation of Bradley, okay.
I'm currently using my phone as my camera, but
Yeah,
I
sure, I
also
saw
need to
you.
use it as my calculator.
Okay. So please next time use maybe need to prepare a separate calculator, okay, for this purpose, okay.
After we turn it in, are we done?
Yeah, you're done. See you
Thank
next Tuesday. You're welcome. Again, please do not copy whatever on the book. Okay, I won't give points if I feel it's just you copied on the book without fully understanding it. I can tell. Write with your own word and using the process we talk about in the class. Okay, the purpose here is just to check to see you pay attention in the lecture. Okay.
Sir, can I ask you a question about the formula real quick?
Sure, go ahead.
I finished with the example, but I just forgot where the value, the 0.05 Newton per second over meter squared, where did that value come from?
That's from the problem statement it gave you. It's a viscosity, viscosity of the oil.
Oh, okay.
Okay.
Thank you.
You're welcome.
Is it okay for us to leave the answer in meters, or do you want it in millimeters?
It doesn't matter. That doesn't matter. Meter is fine. Oh, I always like meter. The millimeter thing, I just try to explain to you what does it, how thick it is actually compared to the width of a hair. Yeah, it's okay, meter.
We can leave after we've submitted, right?
Yes, yes, absolutely.